So the first path A to B, the change in entropy would be dq reversible by T. It's an ideal gas, it's an isotherm, delta U is 0. So dq reversible by T is equal to minus of dw reversible by T. Yes, I can calculate that. So what I need is Q of H. Let's say QH is along the path AB divided by TH. Right? That's the change in entropy that I get over here. And the change in entropy over CD would be QC by TC. So the two isothermal paths. For the adiabats, of course, the change in entropy is 0. So I could write it like that. And now, so I already told you that how to evaluate these heats by saying that delta U is 0 and then going to the work done and get the R, NR, T, natural log V, F by VI. The derivation is given here in the handout, so let's not worry about it. But I encourage that you read it up. But what you get after the derivation is that QH by QC is equal to minus of TH by TC. Now, although we derive this for an ideal gas over here in these handouts and over here, but this is in general true for any reversible cycle. Okay, so this is not just any reversible cycle, not just ideal gas. This is true. Okay, if you wish to derive, we could do it later. So what it gives, essentially, if I put this back, if you wait for 5 minutes, I'll tell you, you could have chosen anything. So now if I put these back over there, then what I get is, right, the change in entropy or delta S comes out to be 0. Yes, I could even do this over the entire path. That comes out to be 0. So for the Carnot cycle, for an ideal gas, I have entropy as a state function. Okay, done. Now, the second thing that I wish to prove is to say that it's true for any material, not just an ideal gas. So, I'll just go back to this figure over here, and this is my engine, that's my refrigerator. Let's say this fellow is A, that's B. And I say, okay, the efficiency, so if I reverse this, it's an engine also. Yes? If I start extracting heat from there, it's an engine. So I say the efficiency of the two engines, A and B, is different. The efficiency of A is greater than that of the efficiency of B. Now, what I say, okay, if that is the case, I'll use this as an engine and I'll use this as a refrigerator. Okay, because the efficiencies are different. And I connect these two. If I do that, I need some work to go in over here. And since the efficiency of this fellow is smaller and this one is more, I need less amount of work to go in to drive this refrigerator, which means by connecting the two together, I have actually generated excess work, which is in contradiction to the second law. Yes? I just connect these two together. The efficiency of this fellow is low, lower than that one. So this fellow needs less amount of work in order to be driven as compared to the work that is coming out. Yes? Yes, no, who was the one asking me? At least not yet. If you don't know, then ask me the question so that I know what to explain. Think of the efficiencies.
Yes, sir. There is amount of extra work multiplied.
Very
But
good.
then how is it contradicting second law? Because there is some amount of heat work with the lower work.
No.
QC would
No.
QC would be positive.
No. I'll make sure that both these things are equal. Both QCs are equal.
Then the efficiency. Heat reservoirs are common.
I make it common, yeah.
But then how would you say that the efficiency?
Exactly, that's what I'm coming to. That two engines cannot have different efficiencies. Two reversible engines cannot have different efficiencies. Right?
Can you define efficiency of a refrigerator?
I should have done that now. Before going on and speaking about efficiencies. So sorry. I mean, I have written it over here, but thank you. So the efficiency epsilon is the work that is done by the engine upon the heat absorbed. Okay, and which is essentially equal to W upon QH. Or if I take the signs into the symbols, QH plus QC by QH